In this lecture, we will discuss about the power in AC circuits and series RLC circuit. So this lecture will cover power in general AC circuit, RLC series circuit, and the impedance triangle of the series RLC circuit. So let us start with the power in general AC circuit. As we all know that most of our AC circuits are inductive in nature. So we can say that in most of our AC circuits, the current will lag the voltage by some angle phi. If we consider that the instantaneous value of the applied voltage is given by this is the instantaneous value of the voltage. So the current would lag the voltage by angle phi degrees, or you can say phi radians. Now, the purpose of this lecture is to obtain the general expression of the active power in AC circuits. Prior to this lecture, we have seen that what is the power in pure AC circuits, such as pure resistive circuit, pure capacitive circuit, and pure inductive circuit. We have also understood the behavior and analysis of the composite circuits, such as series RL circuits, series RC circuits, and like that. Now, in today's lecture, we will see that generally what is the power that is associated with the AC circuits, and the power that we are talking about is the active power, and active power is the power which is consumed. It is the consumed power. Now, because most of our circuits are inductive in nature, for example, your fan, motors, your fridge, your AC, etc. So these are inductive components, inductive appliances. So the circuitries, the AC circuitries are inductive in nature. Now, when we say inductive in nature, we do not mean to say that it is a pure inductor or pure inductive circuit. We mean to say that it is a composite circuit which has a resistance R and some inductance L. So if this is the case, then definitely because of the inductiveness present in the circuit, the current will lag the voltage by some angle phi degree, right? Now, as far as the resistance is concerned, in resistance, the current that flows and the voltage that appears across this resistance, these two will be in same phase. This is the same phase condition. That is, phi here is 0 degree. They do not have any phase difference. Now, as far as your inductor is concerned, in an inductor, the voltage across inductor and the current through it, these two will be having the phase difference of 90 degree, wherein the current lags the voltage by 90 degree. Now, this I and this V are the RMS values here. I and V are the RMS values of V and I respectively. Now, so if we draw the phasor diagram of this particular case, the phasor diagram would be this one, wherein you can see here the voltage VR and the current I are in same phase. The voltage VL is leading the current by 90 degree, and this is the resultant voltage. This is the resultant one, and this is the phase difference, right? So as far as the waveform is concerned, we can represent the same thing in terms of waveform like this. Taking the voltage as the reference phasor, we have this as the reference wave, and because the current is lagging the voltage by 5 degrees or 5 radians, so the current will start 5 degrees after the voltage has started. So this 5-degree phase difference will always be maintained. You can see here, this is 5, this is also 5. Now, what do we want to understand in today's lecture is what is the power. Now, as we know, the instantaneous power is given by P is equal to V into I. So by taking this expression, which we can put here, we have all these expressions which are given in this slide. So the instantaneous power is nothing but it is the product of the instantaneous voltage. That is, we can write here, it is the product of instantaneous voltage into instantaneous ampere. That is instantaneous current. So when we put the relevant values here, Vm sine theta for instantaneous voltage and Vim sine theta minus phi for instantaneous current, we have the equation number 1 here, which is Vm Im sine theta minus phi. So by using the trigonometric rule sine alpha into sine beta, which is this one, we can convert this equation, which is given here, into this equation. So we have cos sine of phi minus cosine 2 theta minus phi divided by 2. So this would be our equation number 2, let us say. Now, how do we calculate the active power? So active power is basically the average power that is absorbed by the circuit. This is also one of the definitions of active power. Now, active power is actually power which is dissipated by the circuit. Oh, right. So we can say absorbed power or dissipated power or utilized power or consumed power. So this is one and same thing. Now, how do we calculate? So we will take the same formula as we use for the average power, so which is 1 by 2 pi into this one. Now, before that, we need to understand this waveform here. So as you can see here, there are two waveforms. This one is for the voltage and this one is for the current and this one is for the power, right? So as you can see here, there are two portions. Now, this is the reference line and we have a shaded portion here, this one. And then we have a shaded portion here, this one, which is negative. So this and this are negative. This and this are positive. Okay. So now, how did we get this curve here? So this curve has been obtained by multiplying the instantaneous values of current and voltage together. And then we got the positive and negative curves of the power. Now, what does it indicate? What does this positive curve and what does this negative curve indicate? This positive curve indicate that the power is from source to load. And this negative indicates power from load to source. So this part indicates the reactive power. So this one is the reactive power, and this one is the active power. Right now, the expression can be obtained by putting these equations here and integrating this from 0 to 2 pi. Now, why we are integrating it from 0 to 2 pi? We can see that our power curve is obtained from 0 to 2 pi. So if we take, let us take another thing here. So it is from 0 to 2 pi radians. So this is how it is. So we will integrate it from 0 to 2 pi, and by integrating this with respect to theta, we have got the expression. So this is how we are solving the equation here. So we can divide this into two parts. One is Vm divided by 4 pi. So this 2 will be multiplied here with this one. So we have 4 pi here. And then we have cos pi, cosine of phi, basically, d theta, right? So this is a constant factor, basically. This one, this is constant. And then we have cosine of 2 theta minus phi d theta. So now here you have integration of d theta as theta, right? And for this you have this one here. So the limits are 0 to 2 pi, and here also 0 to 2 pi. Now as we put these values in the equation, we have got P is equal to Vm Im divided by 4 pi 2 pi cosine of phi. So these two will be, cancelled. This pi and pi will be cancelled. And then we have this equation here, right? Now we have Vm Im by 2 cosine of phi minus this equation. Now if we see the cosine 4 pi minus phi, so this is 0, this is pi by 2, this is pi, this is 3 pi by 2, this is 2 pi, this is again, and then you have 4 pi. So phi is something like here, because the current is, if this is voltage, then this is current. So current is lagging the voltage by angle 5 degrees, right? So sign is existing in the fourth quadrant. So here sign is negative, right? Negative here. So we have this one, then these two will be cancelled, and we have 0. So we are left with this Vm Im by 2 cosine of phi. And if we divide this root 2, so 2 can be written as root 2 into root 2. And so we know that this is known as Vm by root 2 is the RMS value of voltage, which is equal to V. Similarly, Im by root 2 is the RMS value of current, which is I. So we have replaced this with these two factors, and we have got this equation number 3. Now this equation 3 is a general expression of the power absorbed in an AC circuit. So this is the general expression. Now from here you have, if you see, if you take this cosine phi, which is equal to P by VI. So now this P is the active power, and this V into I is the total power, or which we call as apparent power, right? So this is the power factor. Now, even if we do not have the inductive circuits, if we don't have the inductive circuit, we have, let us say, the capacitive circuits, which is the rare case. If we have the capacitive circuits instead of inductive circuit, even then also we have the same expression. Okay, so this expression is also valid for the capacitive circuits. And the reason is because in capacitive circuits, if V is equal to Vm sine theta, then I is equal to Im sine theta plus phi. So because in capacitive circuits, the current leads the voltage by angle phi, right? So if you multiply these two, if you want to get the instantaneous power, which is V into I, so you have Vm sine theta, and then you have Im sine theta plus phi. So you have the similar kind of expression here also. Right? So this is the instantaneous power here. You can compare this with this one, equation number 1, and you need to apply the same, trigonometric rule here also, sine alpha plus sine theta. So by doing so, you will get the similar kind of expression, right? So that is why even if your circuit is an inductive circuit or a capacitive circuit, so you will have the similar kind of expression for the active power of the AC circuit. So let us proceed further. Let us see the series RLC AC circuits. In our previous lectures, we have discussed about the series RL circuit. Then we have discussed about series RC circuit. Now, today we will discuss about a series RLC circuit, which is AC circuit. So let us consider that three components are L and C are connected to one another in series across a voltage source, which is an AC voltage source. So here, this I and V are the RMS values of I and V respectively, where V is Vm sine omega t, which is the instantaneous voltage applied, right? And I is the instantaneous current, which is Im sine omega t plus minus phi. Now, why we have this plus minus phi? Because we may have this circuit as either inductive or capacitive. This we would understand as we proceed in this slide. Now, let there be three voltage drops VR, VL, and VC, which are appearing across the resistor, inductor, and capacitor respectively. So VR is equal to I into R, where VR, if you draw the phasor diagram here, so you can see that VR and I, they are in the same phase. Now here, the voltage VL leads the current by 90 degrees. So we'll draw it like this. The voltage VL leads the current by 90 degrees. And in this case, the current leads the voltage by 90 degrees. So here, this uh, current is the reference phasor. Now, if we have to draw the phasor diagram of this one, how will we draw? We will take current as the reference phasor, right? We know that the VR so we have current and voltage VR which are in same phase. Now, because the voltage VL, it leads the current by 90 degrees, and then we have the voltage VC which lags the current by 90 degrees. So in this particular type of circuit, we are little bit more, now this thing is a little bit more complicated because we do not know whether the resultant phasor of voltage, because current is the reference phasor. Why current is reference phasor? Current is reference phasor because it is common in all three components, that is R, L, and C. So that is why we have taken current as the reference phasor. Now, where will we put the resultant phasor? Whether it would be here, it would be here. That is the question mark now. Now, how will we come to know where we have to put the reference phasor? That all depends upon whether your VL is greater than VC or VL is less than VC. So whichever will dominate. If inductor dominates, then the resultant phasor would be on the upper side. If capacitor dominates, then the resultant phasor of the voltage would be on the lower side. So let us see this one. No. Now let us draw the phasor diagram of this circuit. The phasor diagram for the first case, if VL is greater than VC, that is XL is greater than XC. So this means that the given circuit is inductive and hence the voltage V leads the current I by angle phi. So now let us draw the current phasor. This is, let us say, the current phasor, which is I, and then we have the voltage phasor, which is VR. As we know that in this resistance, the current and this voltage will be, sorry, this current and this voltage will be in phase, right? Now, we also know that the voltage across inductor VL leads the current. Now, in this particular case, we need to understand one thing, because we are taking that VL is greater than VC. So this means that VL minus VC is greater than 0. That is positive. So it will be here. So VL minus VC will be taken on the positive side. So you have VR, you have VL minus VC. So that means there is some net reactive effect. There is some net reactance. Now, net reactance means there may be a possibility that your inductor is greater than capacitor. Sorry, the inductive reactance is greater than capacitive reactance. So there may be a possibility that capacitive reactance is greater than inductive reactance. So in all, you will have a net reactive effect of the circuit, right? So that is why it is said that if this is the case here, if XL is greater than XC, so we can say that the given circuit is inductive in nature. So if it is inductive in nature, so we have this voltage, the net voltage. This is the net voltage drop across the inductor and capacitor. So in this case, you have the resultant phasor that would be here. This is your V, and this is the phase difference phi. So that means in this case, as you can see, the voltage is leading the current by angle phi. So this is the phasor diagram of a circuit in which we have the voltage across inductor is greater than voltage across capacitor, or we can say the circuit, the given RLC circuit is inductive in nature. There may be a possibility that the voltage across capacitor is greater than voltage across inductors. So let us take that case also. Now there is a second case when if VL is less than VC, that is XL is less than XC, then the given RLC circuit, this one, is capacitive in nature. That is, the current I leads the voltage V by angle phi, right? So let us draw the phasor diagram of this one also. So here you have the current phasor, which is I, and then you have the voltage phasor VR, because VR and I are in same phase. Now if we take this condition here, VL is less than VC, or VL minus VC is less than 0, that is negative. So that means the net voltage effect will be appearing on this side, and hence the resultant phasor of the voltage will be appearing here. So this is your V, and this is the phase difference phi. So as you can see here, the current is leading the voltage by angle phi. So this is what happens in the capacitive circuits. So we have all the phasors here. We can see that current I and VR are in same phase. VL minus VC means the voltage, the net voltage across these two components is lagging the current by 90 degrees when your given circuit is acting as a capacitive circuit. Now, In this case, whether it is your capacitive or whether it is inductive circuit, we have seen that the voltage V is basically the phasor of 2. So VR, it is plus minus J, VL minus VC. So it is a complex number. If it is, if the circuit is inductive, V is equal to VR plus J, VL minus VC. If the circuit is capacitive, V is equal to VR minus J, VL minus VC. So that means, now this shows that V is a complex quantity. So let us do its analysis. Now let us come here. In this, as you can see, we have taken V as a complex number. So either it can be plus or minus, both. So the magnitude can be obtained by, now how do we calculate the magnitude of any complex number? If x is a complex number, which is a plus jb, so the magnitude of x is equal to under root the square of real and the square of imaginary, right? So this is what we have done here also. So we have VR square and then we have imaginary part. So this is the imaginary part. And this is the real part. Now, by putting VR, because we know that VR is equal to I into R, that we can see in this slide also here, right? And similarly, VL is equal to I into XL and VC is I into XC. So we have this equation here. So by doing so, we have under root I square R square plus I square XL minus XC square. So this I square will be taken as common. So we have I under root this one. So from here, because the current is the common parameter, so we have current. Now this particular factor under root R square plus XL minus XC whole square is the impedance of this series RLC AC circuit. Now from here we can find out the power factor also, as we know that the power factor is basically the resistance upon impedance. So there are various expressions for the power factor. Power factor is also P by VI. It may be also R upon Z. So both can be taken, right? Both are correct. So we have R by this one. So similarly, if we have to find out the angle phi, this one. So how will we find out? This can be obtained by taking, now let us take this, no, if we draw this as a phasor, so we have this as V reference, this as VR, and then we have this one. This is VL minus VC, right? So this is your angle phi. Now the tangent of this angle tan phi is equal to VL minus VC by VR. So this is what is given here. So we can replace VL with I into XL and VC with I into XC and VR with I into R. So I can be taken as common. You have XL minus XC divided by IR. So I to I is cancelled out. So you have this equation here. So, so from here phi is equal to, now phi is the phase difference, which is equal to tan inverse your XL minus XC divided by R, right? In this, we know this XL is known, XC is known, and R is known, and we can find out this phi, basically. Power factor can be obtained. Now we can see, now this is a short derivation which is given here just to make you understand that this active power is actually the power dissipated. Now from here you can understand this one. In previous slides, we have understood that the power consumed by a general AC circuit is VI cosine of phi, and we know that cosine of phi is R by Z. So if, and V is equal to I into Z for a general AC circuit. So if we replace these two here and this one here, so we have this equation. So here Z to Z is cancelled out. So you have I square R. Now we all know that I square R is the dissipated power. So from here you can understand this concept. Now let us move further. So now we have already discussed these three cases. If XL minus XC is positive, so it will be positive when XL is greater than XC or VL is greater than VC. So in this case, as you can see, your circuit is inductive. Your VL minus VC is positive and phi is positive because phi is tan inverse XL minus XC by R. So if XL is greater than, this is greater than this one, so it is positive. Similarly, we have the second case wherein the XL minus XC is negative. So this would be negative when your VL is less than VC, right? Now you can see it here in this slide. If VL is less than VC, so VL minus VC is negative, right? Now, so in this case, circuit is capacitive and your VL minus VC is negative and phi is negative, and we can say that I leads V by phi, and here I lags V by phi. Now, what about this one? What about this condition when XL is equal to XC? So this is a very important condition. Now, if we see Z is equal to under root R square plus XL minus XC whole square, if XL is equal to XC, then Z is equal to R. Now, what is this? Now, we will study next class. Right? Now, let us come to the impedance triangles. Now, the impedance triangle, this is the case when your XL is greater than XC. And this is the case when XL is less than XC. Right? So here XL minus XC is greater than 0, that is positive. Here XL minus XC is less than 0, that is negative. Right? So this can be drawn from the voltage triangle also. As you can see in this voltage triangle, if you take this voltage triangle and you let us take the voltage triangle for inductive case, right? So here you have the resistance voltage, then you have the net voltage VL minus VC, and then you have the resultant voltage V and then angle phi. Now, if you divide this with I, which is the common factor, so this can be taken as, because V by I is Z, VR by I is R, and VL minus I, VC by I is nothing but it is XL minus XC. So this is for the inductive case. Similarly, this is for the capacitive case. This is for capacitive case. Now, this can be also be drawn. You can see here in this diagram, you have VR and V and VL minus VC. So let us draw. So we have VR, then we have VL minus VC, and then we have V. This is phi. Now in this diagram, you can see if you divide this with I here and I here and I here, so you will have VR by I is nothing but R, and then this is nothing but XL minus XC, and then you have the impedance set. So this is how we have obtained these two impedance triangles, right? So that means in series RLC circuit, we need to take the net effect of the reactance in the circuitry. So this was all about today's class, and thank you so much.